Whenever we're looking at numbers that are representing measurements, the digits in the number are going to be significant depending on the instrument that it's being used to determine that measurement. So I have two examples here on the top of the page. One is just a ruler, and then the other one it's representing a digital mass balance. So when we're looking at the ruler, the first example, the increments in the ruler are by 0.1. Okay? So we start at 0, and then we have 0.1, 0.2, 0.3, 0.4, 0.5. I have labeled that one in the ruler, and then you can keep counting by 0.1s until you get to 1. So you go from 0.5 to 0.6, 0.7, 0.8, 0.9, and then we have 1. Okay? So the scale on that ruler is measuring by 0.1. Okay? So that's that decimal place, the 0.1 or that first decimal place, it's something that you can actually measure using this ruler. So I have two lines, the pink and the green one. The pink one, you can see that it's right before 0.4. It's not exactly at 0.4. It's a little bit shorter than that distance of 0.4, and I'm using units here of inches. So your ruler, it's measuring that 0.4, right? It's measuring 0.1, 0.2, 0.3, 0.4, 0.5, and so on. Now, what we can do whenever we have a scale like this one, this ruler allows you to measure that first decimal place. The second decimal place, it's something that we can estimate. Okay? So the pink line right there is not at 0.4, it's a little bit shorter than 0.4. It's longer than 0.3, but shorter than 0.4. So we can estimate we can measure the first decimal place, and then we can estimate a second one. So for my pink line right there, this is my 0.3 here, this is 0.4. So I know that it's longer than 0.3 and it's a little bit shorter than 0.4. So I'm going to estimate my second decimal place right there. So for the green line right here, again using the same scale, increments of 0.1, you have labeled the 0.5. This one here will be 0.6, 0.7. So my green line is between my 0.6 and 0.7. Okay? So you can estimate, right? You know that the 0.6 it's measured by a ruler. So you can estimate that second decimal place in that measurement. That's by estimated digit. So this is something that happens when you have analog instruments, that when you're using an analog instrument to take a measurement. The one on the right side, my sketch on the right side where I have a mug, that's representing a mass balance. It's a digital mass balance. So when you're using a digital instrument, all of the digits right there are actually significant. Your measurement has all of those digits as significant. The difference between the one on the left and the one on the right, right? The one on the left, you're measuring a decimal place, right? In my examples, right, you have 0.3, 0.39. The second one is the estimated one. In the digital one, you are not estimating any digits. All of them are given. Your measurements, they still have an error associated to them. In my example for the ruler, the one that I'm using to measure the inches for your pink and green line, the second digit that I'm estimating, that second decimal place, it carries an error. Okay? I'm measuring 0.39, I'm measuring 0.66, but my estimate can be a little bit different from someone else's estimate. So that estimated number carries the error. For the mass balance, the same thing is true. My last digit right there, 0.752, the last one is the one that carries the error in that measurement. But for both examples, on the first one, both numbers are significant. The 0.39, those two digits are significant. 0.66, those two digits are significant. When we look at the measurement on the right side for the mass balance, we have a 0 and then we have 0.752. So to determine which digits are significant and which ones are not, we have rules. The first rule is the easiest one to remember. Any digit in a number that is different from 0, it's always significant. So looking at my examples, I have 0.39, 0.66, 0.752. We're looking at digits that are different from 0, but we're going to have rules that applies for the different types of zeros that you can have in a number. But just looking at the first rule that you have right there, 0.39, the 0, we still don't know if it's significant or not, but the 3 and the 9, both digits are different from 0, so both digits are going to be significant. On the right side where you have 0.752, the 0, we still don't know if it's significant or not, but the 7, the 5, and the 2, all three of them are significant, and that's based on my rule number 1. So I have some examples here. I have 317, 317. All three digits in that number are different from 0, which means that that number right there has 3 significant figures. The 3, the 1, and the 7. The second number, 42, the 4 and the 2, both of them are significant figures. The last one is a number in scientific notation. So when you're looking at scientific notation, your exponential part, we don't look at the exponential part to determine how many digits are significant in that number. So that number 2.3 times 10 to the second, to determine the number of significant digits, we're looking only at the decimal part. So 2.3, that's 2 significant figures too. So for the second rule, we're looking at the zeros. When you have zeros in a number. So we have 3 groups for your zeros, or 3 categories. The first one, it's confined zeros. Confined zeros are any zeros that you have in a number between 2 digits different from 0. When you have confined zeros are always significant. So if you're counting the total number of significant digits or significant figures in a number, and you have confined zeros, all of them are counted towards the total number of significant figures. So I have 2 examples. 3067. So So I'm using the blue right here, and that 0 right there, it's a confined 0. It's between a digit equal to 3, right? Your 3 is the first digit in your number. Then you have that confined 0 because it's between 3 and 6, 2 digits different from 0. So that confined 0 is significant. And when you're counting your total number of significant figures, you have to include that one. 1, 2, 3, and 4. Now in the second example, I'm using a very similar number. That's your first significant figure, the 3. And then you have all of these zeros here between the 3 and the 6. All of those zeros are confined zeros. All of them are between your digit 3 and your digit 6. So all of them are counted as significant figures. So for that last example, the 3, the 6, and the 7 are significant. So that's already 3 significant figures. And then all of your confined zeros, which are 3 of them, are going to give you a total of 6 significant figures. So you have 1, 2, 3, 4, 5, 6. So that's the first type of zero, confined zeros, and they're always significant. The second type of zero that you can have in a number are leading zeros. Leading zeros are any zeros that you have in front of the first digit different from 0. All of the leading zeros in a number, all of them are not significant. The leading zeros are just telling you where the decimal point is. If you convert a number with leading zeros to scientific notation, you are not including those leading zeros in your number when you put it in scientific notation. And you don't include them because they are not significant. So leading zeros right here in my first example, the first digit different from 0 is that 4. In front of that 4, all of the zeros that you have are leading zeros and they are not significant. You can convert that number to scientific notation and you will get 4.33 times 10 to the minus 4. And you're not including all of the leading zeros in your number in scientific notation. So when you're counting your number of significant figures for this example here, 1, 2, and 3, because your leading zeros are not significant. So on the second example, you have the first digit different from 0 is the 8, right there. Any zero in front of that first digit different from 0 in the number are leading zeros and they are not significant. Now you also have another type of 0 in that number, which are your confined zeros right there. So for your confined zeros, you have 2 of them in that number, and those 2 confined zeros are significant. The leading zeros not significant, but the confined zeros are significant. So for that number, you have a total of 4 significant figures: the 8, the 2 confined zeros, and the 3 at the end. The last type of zero that you can have in a number are trailing zeros. So you have 3 types: confined zeros, always significant; leading zeros, always not significant; and then trailing zeros, which can be significant or not significant. There's an easy way for you to determine if your trailing zeros are significant or not. Now, trailing zeros are all the zeros that you can have at the end of a number. So you're looking at the number, the last digit different from zero, and then any zeros that you have after that digit are going to be trailing zeros. If you have a decimal point, explicit decimal point, all of the trailing zeros are significant. You know that if you have a number with no decimal point, you know that the decimal point is at the end of the number. But that decimal point, if you don't get to see it, is not an explicit decimal point. You know that it's there, but it's not being shown. So when you do have an explicit decimal point, you're going to count your trailing zeros as significant. So looking at my examples, the first example is 100. The 1 in that number is significant because it's a digit different from 0, so it's always significant. And now you have two zeros after that 1. Those two zeros are trailing zeros. Okay? Your trailing zeros at the end of a number. So those are trailing zeros. Now, are they significant or not significant? You're looking for a decimal point. You see, in that first example, you don't have an explicit decimal point, which means that if you don't have an explicit decimal point, those trailing zeros are not significant. And that number has just one significant figure. The second example is still 100. It's the same number, okay? 100. The difference between the first one and the second one is that on the second one, you do have an explicit decimal point. It's right there. Since you do have an explicit decimal point, those two trailing zeros are significant now. And that number has three significant figures. The next example is still 100. You see, all of my first four numbers in your list of examples, all of those four numbers are representing the same magnitude, 100. What is different between them is the number of significant figures that you have for each one. So on the third one, you do have an explicit decimal point right there in that number. Your trailing zeros are not just the zeros after your decimal point. Your trailing zeros are all the zeros that you have at the end of a number. Your number, the first digit that is different from 0 is the 1, and that's the last digit that is different from 0 too. All of the zeros that you have after that 1 are trailing zeros. The ones before the decimal, the one after the decimal point. All of them are significant because you have an explicit decimal point. So you have four significant figures in that number. The 1, and then you have your three trailing zeros that are significant because you have an explicit decimal point. The next one, still 100, but now you have two zeros after that explicit decimal point. So you have in total four trailing zeros, four of them, plus 1, your first digit different from 0, which is the number 1. So that will give you a total of 5 significant figures. And the last example that you have for trailing zeros, 1.250 times 10 to the third. Remember, when you're counting number of significant digits or significant figures, The exponential part in scientific notation, we don't use that part. We're looking at significant figures on that decimal part in your scientific notation. So we're looking just at the 1.250. Now in that example, you have one trailing zero. You see you have an explicit decimal point, 1.250. Your decimal point is right there between the 1 and the 2. And then at the end, you have a 0. Since you have that 0 with an explicit decimal point, that 0 is significant. And that number has 4 significant figures. This is the rule for rounding, and we're going to do some examples where we have to apply the rule. Okay? So if you're rounding a number, like the last digit that you want to keep in a number, it's followed by a number that is equal to 5 or higher. When you're rounding that last digit that you want to keep up. Okay? So I have an example. Several examples. The first one, 25.8, we're rounding that one to 2 significant figures. If you're rounding to 2 significant figures, the first significant figure is the 2, the second one is that 5. So we're rounding to 2 significant figures. The digit that you have after that second significant figure, the one that I want to keep, it's an 8. Okay? So you have 25.8 and you're rounding to 2 significant figures. So that digit after the 5 is an 8, which means that when you're rounding, you have to round up. So your number here rounded to 2 significant figures is going to be 26. Now for the second example, again rounding to 2 significant figures. So the first one is the 2, the second one is 5. So you have 25.3. So the digit that follows that digit, the last one that you want to keep, which is the 5, it's a 3. So it's smaller than 5, so we keep the number as it is. We round to 2 significant figures, but we don't round up. So this one here will be 25. Now the last one, we're rounding to 2 significant figures. In your number, the one that I'm showing you there, you have leading zeros. The leading zeros are not significant. In that number, the first significant digit is the 8 and then 3. So you're rounding to 2 significant figures. All of your zeros are not significant. Then we have 8. And then the last digit that you want to keep is the 3. And that 3 is followed by another 3. Since that number is smaller than 5, you don't have to round up. You keep that number as 0.0083. So these are the basic rules for assigning significant figures, how many significant digits you have in a number. Now, those rules by themselves are not giving you a lot of information. We actually use those rules when solving mathematical operations, okay? Addition, subtraction, multiplication, or division, all of them. So we have two rules, one that applies to addition, subtraction, and then another one that applies to multiplication and division. When you have a mathematical problem involving addition and subtraction, we are writing the final answer with the proper number of significant figures. But to determine what's the proper number of significant figures that you have to keep at the end, you need to look at the decimal places. And this is only for addition, subtraction. Your final number is going to have as many decimal places as the number with the fewest amount. So I have an example here. The first number, you have 2 decimal places. On the second one, you have 3. On the last one, you have 5 decimal places. So 2, 3, and 5. The rule is telling you your final number needs to have the same number of decimal places as the number with the fewest amount. The number with the fewest amount of decimal places is that one right there, 7.20, 2 decimal places. So I'm going to add my numbers in the calculator. 7.20 plus 3.013 plus 0.04327. I'm going to copy the whole number that I have in the calculator. 10.25627. That's what I'm getting from the calculator, but that's not the correct answer. Your final answer needs to have the same number of decimal places as the number with the fewest amount. 2 decimal places. 2 decimal places here. And you're keeping 2 decimal places. So if you're keeping 2 decimal places in your last answer, right, you have 0.25. That 5 is the last digit that you want to keep, and it's followed by a 6. So you have to round that 5 up because it's followed by a 6, a digit that is higher than 5. Now, you see how I'm looking at the decimal places to determine how many decimal places I'm keeping in my final answer. Depending on how many decimal places you're keeping in your final answer, you're going to have a specific number of significant figures. So that number 10.26, 1, 2, 3, 4 significant figures. It's not just the decimal places. You're looking at the decimal places to determine how many of them you're keeping, and depending on how many decimal places you're keeping, you're going to have a total number of significant figures in your number. The second rule is for multiplication and division. Now, when you're looking at mathematical operations involving multiplication and division, we don't have to look at the number of decimal places. Now we're looking at how many significant figures you have in each number in your mathematical operation, okay? So just significant digits. So the first example here, I have 101 times 32. So you have to remember your rules on how to determine how many digits are significant in a number. That you need to know. So when you do 101 times 32, I'm going to write down how much is that when you do that in your calculator. That's from the calculator. The rule is telling you your final answer is going to have as many significant figures as the number with the fewest amount. First number here, 3 significant figures. 101. Confined 0 is significant. Second number, 32, two significant figures. So it means that your final answer needs to have two significant figures because you need to keep as many as the number with the fewest amount. So two significant figures, 1 and 2. The last number that is significant in that the last digit that is significant in that number is these two right there. Just two significant figures. So there are two possible ways or two correct ways of getting your final answer. Your final answer is not 32. You cannot drop the last two digits to get your final answer because the number is 3,232. If you just write down 32, 32 it's 10 times smaller. 1,000 times smaller, not 10. 10 times 32 is just 320. 1,000 times smaller than 3,232. So you cannot write down your final answer as 32 because that's not even close to the actual number that you're supposed to have. Your two possible ways of writing this answer here is like that. That's 3,200. That number represents the same magnitude in the thousands as the number that you're getting from the calculator, but it's the number with the correct amount of significant figures. This is one way. Another way is to convert your number to scientific notation. You see, 3,232 is the same as 3.232 times 10 to the third. Those two numbers are representing the same thing. Now, you still need two significant figures in your number, so you can just round this one. So this number here is correct. This number here is correct. So either one is representing the final answer in the correct number of significant digits, not 32. You remember 32, it's 1,000 times smaller than the answer that you're getting from the calculator. So you cannot just round that number to 32. You need a number in the thousands with two significant figures. So whichever one you prefer, both of them are representing the same thing. The first one that I have in the box, 3200, is the same as 3.2 times 10 to the third. They're representing the same thing. Now the second number, right, the second problem right there, 108 divided by 12. 108, you have a confined zero. That's a total of three significant figures. And then 12 is just two significant figures. So when you do 108 divided by 12 in your calculator, the calculator is going to give you that 9. Now, you need two significant figures in your final answer because 108 is three significant figures, 12 is two significant figures, and you need to have in your final answer as many significant digits as the number with the fewest amount, which in this case is 2. So 9 is not the correct answer because for 9 you have only one significant figure. So the correct answer is 9.0. 9.0, you have a trailing zero that is there after an explicit decimal point. Since you have an explicit decimal point, that zero, trailing zero at the end, is significant. Now the last one, you have 25 times 4. 25 is two significant digits. 4 is just one significant figure or one significant digit. So when you multiply 25 times 4, that's 100. When you do 25 times 4, 25 two significant digits, 4 just one significant figure or significant digit. So 100, you have 3 digits in that number. But out of your 3 digits, only one is significant because you don't have an explicit decimal point. And since you don't have an explicit decimal point, these two trailing zeros here are not significant. Now I have here two examples that are combining different mathematical operations. So you have to actually apply the rule for addition, subtraction, and also the rule for multiplication and division. So when you're solving a problem like this, you will see that I'm going to write down my numbers, all of them. I'm not rounding between steps. You cannot round between steps. You need to keep track as how many significant figures you have in your numbers when you're done with your steps, but you cannot round the numbers. So I'm going to start the first one here. Let me put letter A for this one. So I'm going to start with what I have in the parentheses, which is a subtraction. I'm going to get the number from the calculator, everything, 5.489 minus 5.01, 0.479. See, I'm not rounding, I'm just writing down my number as it is in the calculator. Now, that's a subtraction. You have a number 5.489 with 3 decimal places. 5.01 is a number with 2 decimal places, which means that I'm getting a number right there with 3 decimal places. Out of the 3 decimal places, only 2 of them are significant because you have 2 decimal places in that number. So only 2 of them are significant. You're not dropping that 9 at the end. You're not rounding your number because we cannot round between steps. We can round only the final answer, and that's not the final answer. That's just the solution for what you have in the parentheses. So you know that you're getting 0.479, but out of your 3 decimal places, your 3 digits in your number, not all 3 of them are significant. Based on your rule for addition subtraction, you need to keep as many decimal places as the number with the fewest amount, which in this case is just 2 decimal places because you have 5.01. So out of the 3, only 2 of them are significant. Now we can move to the multiplication. That number times 5.903 times 6.78. So you see now all of your 3 numbers are being multiplied. So now we're looking at the rule for multiplication. 6.78 3 significant figures. 5.903, 4 significant digits. Then your last number is 0.479. The zero is a leading zero, and leading zeros are not significant. So you have 3 significant figures in that number. No, three digits in your number. Out of the 3 digits, only 2 of them are significant. The ones that I have underlined right there. Remember, only 2 because you have 2 decimal places in that number 5.01. So out of the 3 digits, only 2 are significant. So when you're doing your multiplication, 6.78, 3 significant figures, 5.903, 4 significant figures, 0.479, that's 3 digits, but out of the 3, only 2 are significant, which means that your final answer, the total number of significant figures that are significant, is determined by this one right here. Only two significant figures. So I'm going to do in the calculator 6.78 times 5.903 times 0.479. I'm not rounding that number, I'm using that number as it is, 0.479, but knowing that out of the 3, only 2 are actually significant. So I get 19.170700086. But out of all of that number, only 2 digits are significant. And the final answer for this problem is 19. Second example, what I have first, it's a multiplication. So 5.4 times 0.916. So I'm going to write down the whole number, everything that I have in the calculator, 4.9464. Now, that's a multiplication. When you're multiplying, right, you're keeping as many significant figures as the number with the fewest amount. 5.4 is 2 significant figures. 0.916, that's 3 significant figures. So out of your whole number, 4.9464, only 2 digits are significant. This is the one with the fewest amount of significant figures. That's a multiplication. So only 2 digits are significant. The first digit is 4, the second digit is the 9. So the whole number is there, but you need to keep in mind that from that whole number, only 2 digits are significant, which are the first 2. So now when you do the last part of your problem, it's a subtraction. You see, you have 19.667 minus 4.9464. We're not rounding the number, we're keeping the number from that multiplication as it is, just knowing how many digits in the number are actually significant. So when you're subtracting your numbers here, the first number, 19.667, you have 3 decimal places, and now I'm looking at the decimal places because this is a subtraction. The second number, you see, you have 4 decimal places, right? 9464, 4 decimal places, but out of the 4 decimal places, only one of them is actually significant, which is the 9. All the other 3 decimal places are not significant. So when you're doing your subtraction here, your final number, you need to keep only 1 decimal place determined by this number right here. So 19 0.667 minus 4.9464. I'm going to copy the whole thing that I have from the calculator, but that's not the final answer. The final answer, you need to keep only one decimal place, which means that your final answer has to be 14.7. Here you have some examples. Make sure that you work them out, copy your answers, and then you can check the answer key for the solution.